Hello, everybody. We are Team 2 with the spring term of ME452 Design for Manufacturing. Our team has chosen to analyze and redesign a pencil sharpener. Pencil sharpeners are used for sharpening wooden pencils. This model is hand crank operated, which rotates a helical blade to cut wood and graphite at a consistent angle. This provides a reliable and usable writing edge, and pencil sharpeners are used by students as well as educational and industry professionals. This model in particular also has a self-contained shaving collection compartment, pencil grip, and guide. Our primary customers come from the education sector, like schools, colleges, and universities, which all have a need for sharpening pencils to ensure that students have a reliable and usable writing instrument. Our secondary customers are industry professionals, professionals in creative fields, architects, designers, artists, and engineers alike all rely on pencil sharpeners to ensure that their pencils can quickly be restored to a usable condition so that they can continue their work. Regarding the market share, we are targeting the domestic market in the United States, where the annual demand for pencil sharpeners is approximately 3 million units. Our goal is to capture a significant portion of this market share, aiming for an annual production volume of 100,000 units.
Next, we have the functional analysis, with our task function being sharpen pencil. Branching off from that, we have two primal basic functions, cut pencil and contain pencil. Branching off from cut pencil, we have the basic functions transmit torque and remove material. And branching off of contain pencil, we have the basic function center pencil. Branching off of enhanced product on the bottom of the chart, we have two supporting functions, collect shavings and grip pencil, and all of these functions come together to create our product. Next, we have the assembly sequence analysis. In the top assembly, it starts with the body, and we assemble the main sharpening unit as a sub-assembly and place it into the body and assemble the rest of the sharpener as seen in the diagram on the top. And in the second assembly on the bottom, we start with the main sharpening unit using the pencil slot as our starting place and assemble it piece by piece as seen in the diagram. Ultimately, we decided that sequence 1 was better for assembly. Next, we have the function component mapping matrix with the 5 functions at the top being transmit torque, remove material, grip pencil, collect shavings, and center pencil. And one thing to note is that the body does not have a function mapped to it, which means it can be better redesigned in the future.
This is our bill of materials. Our calculated cost is based on an annual production of 100,000 individual pencil sharpeners. Manufacturing costs for injection molding, machining, and sheet metal processes were calculated using the methods covered in class. The manufacturing cost for the die-cast components were estimated using the website custompartnet.com. We assumed that the pencil sharpener was manually assembled, and we estimated that the factory workers would be paid an average of $20 per hour. The total estimated cost to manufacture one pencil sharpener is $9.59. This is a comparison of component cost and functionality. The component is considered high cost if its total cost is 50 cents or greater, and low cost if it's below 50 cents. Component functionality was determined using the functional component mapping matrix on slide 6. The mapping matrix identified the crank handle, pencil grips, and pencil grip frame as low functionality.
Our final analysis was about the product family, where we compared our crank pencil sharpener against a motorized. The shared functions between these two were almost the same, with the only custom function between customer groups was detecting pencil for the motorized. Because of this, the platforms were almost exactly the same, where the only modules were a motor and a sensor for our variant, and the crank and a handle are the original. On the next slide, we can see a nice exploded view of how these modules will be interacting with the components that will actually be sharpening the pencil. And on the slide after that, we can see a nice exploded view of all the parts that would be shared between both the motorized and the crank variants of this pencil sharpener. The final thing to look at is where delayed differentiation would be happening, and that is on the final slide. We have our fishbone analysis on top, where we can see the sharpening mechanism is inserted into the body, and this gives us about 6 steps before the differentiation happens, as that's where our actuator, our crank, or our motor needs to then be inserted. Because we have so many platforms in this, we were able to optimize this by finishing all of the body's assembly before working on and finishing the sharpening components of this, and that led us to only 4 steps before the differentiation actually happens. This has been the end of our presentation, and thank you for your time.